And I think CI's model as well.
Yeah, that's got a few sentences, right?
I didn't know it was on, so I worked on my sheet.
Yeah, I forget the name of the person.
Oh, thanks.
New people who've just
Oh, that's Jen.
yeah, and Rob joined and operate.
Oh, wow.
Find stuff that's getting knowledge and stuff.
Janice.
That doesn't sound very helpful, Patrick. Oh, yeah, it's much better. Oh, is it? Yeah, I got some hydrogen over.
I think so.
The video, we had a...
Sorry?
Would you mind playing just the first... Well, we have...
Oh, you have a video?
Yeah, but it's from YouTube, and we started... I thought if you press the button, it would appear. No, it's not on there.
So it must be that one?
That's the one. But we couldn't get any sound.
Oh, no, it's not back, is it?
Yeah, there should be sound.
Yeah.
Okay, so we'll get started if I can call you to attention. It was suggested to me I should start with a joke, but I'm a lousy comedian, so I won't. My name's Helen Clue. I'm the Deputy and Science Director of the Oceans and Atmosphere Flagship, and it's my great pleasure indeed to welcome you here today to CSIRO's Aspendale site. In particular, I welcome Tony and other members of the Priestley family this afternoon. Wonderful to have you here. I'd like to pay also my respects to the Bunurong people, past and present, the traditional custodians of the land on which we meet today. Just very briefly, I should also let you know about our emergency evacuation procedures in case it should be needed. My best advice to you, as I said to those that were here this morning, is to actually find a CSIRO person and follow them. But failing that, the directions are to exit out of either of the two doors and make your way towards the area outside the canteen. If there is an emergency, there may even be people around with hard hats on, so follow them too is probably a good idea. And if you need toilet facilities, they're out this back door here and a hard right, and they're just over there. And just to remind you that you're all welcome to stay on after this occasion and join us for reception and refreshments, I think is the correct phrase in the canteen. Okay, so you're here today, of course, to hear the 2015 Priestley Lecture. This is a series of lectures that started in 1995, which actually means this is an important date. It's the 20th, although there's going to be a debate because someone else told me it was the 21st, but I'm convinced that it's the 20th of the Priestley Lectures, which, of course, honour Bill Priestley, the founding chief of CSIRO's former atmospheric division. In his portrait, you can see there on the back wall, along with other chiefs of the division under various different names, which are hanging around the walls of this lecture theatre. CSIRO in Aspendale, we don't just honour our chiefs and our site leaders, we also honour those retired staff who have contributed long and loyal service to CSIRO. And for those of you who are wondering, what does it take to have your portrait on these brick walls in this theatre? You need to have served in CSIRO for at least 30 years. So the time has come to honour 3 more of our Aspendale colleagues and induct them into what we might unofficially call the Aspendale Hall of Fame. So the 3 that we're inducting this year from CSIRO are Janice Bathols, who served in CSIRO for 46 years, Paul Fraser, who served in CSIRO for 40 years, and Rob Gillette, who served for 38 years. And I'm actually just, because there's 3 of them, I can actually say a little bit about each of them, which I will now do. And I can say that their portraits are hung over there. They're about in the middle underneath that light here, right beside Ian Galbally, actually, are the 3 portraits. So a few moments just comment on each of our 3 new inductees. I was going to call them hangings, but then I thought that didn't sound very good. That's my only joke, okay. It's an absolute delight to be able to induct Janice into our Hall of Fame. And I'm sure you're all aware of one of the reasons why it is an absolute delight. If you cast your eyes around the wall, you can, as I have sat for many hours, as many of you have, will have noticed that the gender balance does not at all match current standards, except perhaps for the current cabinet, but I didn't say that. So it's fantastic to be able to welcome a female, a woman scientist into our Hall of Fame. But not just because of that. Janet is one of those, I think we could call her a quiet achiever, but without whom CSIRO and our science here at Aspendale just would not happen. She's been involved, I went and looked back in the projects that she was involved in, all sorts of projects, too many to list here. She's been a co-author on dozens of reports and papers. She's been a member of several award-winning teams, and I just wanted to acknowledge her most recent outstanding contribution, which was as part of the team delivering the latest suite of climate projections for Australia, regional projections for Australia, the so-called NRM project, which was delivered early this year and is truly an outstanding piece of work. So Janice, 46 years, she started in, I've got 1969 here to 2014. I hope I've got those dates right. Our second, Paul Fraser. Paul was in CSIRO for 40 years. He joined in 1974 as an experimental scientist and became a CSIRO Fellow in 2012, which, as you would know, is the most senior research scientist position that you can reach in CSIRO. Paul's outstanding research career and his contributions addressing global change, but focusing on the physical and chemical factors that influence climate change and ozone depletion, his work is well known to everybody in this audience. Paul's published over 230 papers and won many, many awards, and he is Fellow of the Australian Academy of Technological Sciences and Engineering. And Paul continues to have a relationship, which we're all delighted about, with CSIRO as an honorary Fellow. So Paul is our second inductee, and Rob Gillette is our third. And Rob's been in CSIRO for 38 years, 1977 to 2015. Rob was a research project officer with our various teams. I'd describe Rob as another of our quiet achievers without whom, there he is at the back, without whom we just couldn't have done what we did. He's again been involved in many, many projects. I guess in the time that I've been involved with Aspendale, Rob, as a truly highly skilled chemist, has provided outstanding support to our air quality research, but I do know that he's been involved in Cape Grim activities and many other projects as well. And like Janice, he has been a member of award-winning teams as well. So it's with great pleasure that I induct the portraits of these retired staff, between them over a century of service to CSIRO, into the Aspendale Lecture Theatre, the Priestley Lecture Theatre. So join with me in congratulating them. I hope you're enjoying the pictures behind me, by the way. And I hope afterwards you can go up and congratulate them in person. So this brings me to the Priestley Lecture. And as I know you all know, this lecture theatre and the workshop is named in honour of Dr. Bill Priestley. This is a very special year, not just because it's the 20th Priestley Lecture, but it's also just short of 100 years since Bill's birth on July the 8th in London. So it's a centennial of his birth. So it's a very special day indeed. The history of Bill's contribution to CSIRO, I'm just going to go through quite, because I think it's important for those who are new. Bill was appointed to the position of officer in charge of a new section in the then CSIR in Australia in 1946. And in doing the little bit of research that I did last night, and here I do hope that my source is correct, that I gather that there was some discussion about where this new section should be. Should it be in Sydney or should it be in Melbourne? And that he selected Melbourne as the new site because he believed that the research would benefit from the closer proximity to the Bureau of Meteorology. And of course, we now have recognised that importance of that relationship with the Bureau of Meteorology by forming a partnership with Bureau called Corker. So he was prescient indeed. The Meteorological Physics section, then became the Division of Meteorological Physics in 1955 and then the Division of Atmospheric Physics in 1971. And again, I hope I've got all the dates and names right. Bill retired as chief of that division in 1972 and retired from active service in the late 80s, and he died in May 1998. As I know you all realise, Bill was an intellectual giant in his field of atmospheric turbulence, but large-scale circulation as well. And he was a successful, what I think of as the founding chief of the division that's gone through many names, but the division that's been the home, or the business unit that's been the home of atmospheric research in CSIRO over many, many decades, from the Division of Atmospheric Physics, under Bill's leadership, to the Division of Atmospheric Research, and then Marine and Atmospheric Research, and now Oceans and Atmosphere, and possibly I've missed a name in there somewhere. But I guess the thing that we can all note, those of us who are atmospheric scientists, is that the one continuity in there is the word atmosphere, so that's good. And so Bill really had such an important role in founding the research and the science that's been done here at Aspendale. And we've had a workshop today. For those who've just joined us now, we've had a fantastic set of talks today, and many of the speakers did comment upon their links to Bill himself or their links to people who themselves were influenced by Bill. In other words, multiple generations of people who we can trace their choice of career and what they've done back to the leadership that Bill Priestley provided. I was interested to note that according to Cyropedia, the source of my knowledge, which I hope is correct, that the decision to set up the new section called Meteorological Physics in the then CSIR was motivated by a view then by the leaders in CSIR that there was more research required into what was seen as being a big constraint on the growth and development in Australia, which is water. And although Bill might not have thought of it as his most significant piece of work, I just wanted to make a comment about a paper that he co-authored in 1972, become quite a famous paper, the Priestley and Taylor paper. It's a classic example in my view. I mean, his contribution is huge and I could spend half an hour talking about it, but it's a great example of the joining together of his understanding about large-scale processes, but his interest and the emerging interest that, of course, was coming through in the 70s about the importance of exchanges of heat and water with the underlying boundary, whether it was water or land. And bringing those two interests together, he co-authored a paper entitled On the Assessment of Surface Heat Flux and Evaporation Using Large-Scale Parameters. And he proposed, based on energetic considerations, an expression, a very simple expression, for how we might quantify land surface evaporation. The Priestley-Taylor formula is still used today. And this is where the link comes to me, because I did my honours thesis evaluating the utility of the Priestley-Taylor equation for, at that point, irrigated grassland, but subsequent work I've done over the years has continued to explore how we can quantify land surface evaporation. It also connects Bill's legacy not just to me personally, but for those of you who don't know, I'm based in CSIRO in Canberra with the group that used to be the Centre for Environmental Mechanics, and of course Bill had a bit to do with that as well, including its former chief. And of course, the Centre for Environmental Mechanics did a range of different work, but our interest where I'm from is from the micrometeorology side, the land-air exchange side. And certainly when I was an undergraduate, the research that came out of Aspendale and environmental mechanics on surface layer exchanges and processes were incredibly formative in me choosing my career. There's also a link that I want to bring here to a particular area, which is that our colleague, Mike Raupak, in the early 2000s actually published some very nice papers, again providing the theoretical basis for why this energetic approach to land surface evaporation works. And I guess I wanted to use today just to acknowledge, as I know you're all aware, that Mike died earlier this year. Mike also was an absolute intellectual giant, and I know that many people in this audience have worked closely with Mike over many years. He had a huge influence, again, on atmospheric turbulence, but work on carbon budgets, climate change, earth system science, and I know Mike was a close colleague to many of you here today, and we all miss him greatly, and I just wanted to pay tribute to Mike as well today. So back to Bill and his legacy. I think it's interesting that CSIR and the section that he started said about the importance of water, because I think today, in 2015, that link between climate change and water is as critically important today as it was back then. Whether it's because of the ongoing debate that many of us here understand, where people are debating about how the hydrological cycle will respond to global warming, or whether it's thinking about, well, what is going to be the impact of that interchange between climate variability and climate change on water availability in Australia. And we heard talks today about some of those drivers, ENSO, IOD, and so forth. So it's still an important area today as it was then, and that's my segue to bring us to today's Priestley Lecture, which we're truly delighted to be joined by Dr. George Philander, who is Professor of Geosciences at Princeton University. I know that George is very well known to many of you in the audience. He has held senior positions at the Geophysical Fluid Dynamics Lab, or GFDL as we all think of it, with NOAA in the United States. And he's held senior positions in South Africa as well. He's won many awards. He's a fellow of the American Meteorological Society, the American Geophysical Union, the American Academy of Arts and Sciences, and a member of the US National Academy of Sciences. And he holds a Doctor of Science from the University of Cape Town. He's a world-renowned ocean atmospheric researcher. His research has made enormous contributions to our understanding and modelling of large-scale climate variability, including La Nina and El Nino and other phenomena, and we've heard a lot about his contributions today. He also has research interests focusing around paleoclimate and ice ages. And I was intrigued to note, actually, when I was doing a little bit of research on George over the last couple of days, that he's actually on the board of an initiative called Access. Not our Access, which is our climate and earth system model, so our name has been is also known for something else. Access is the Applied Centre for Climate and Earth System Science, and reading what the purpose of that centre is, it's ambitious and really exciting about providing integrated end-to-end research and education and training, outputs and outcomes relating to the area that we would think of as earth system science. And I think for many of us here today, and in particular myself, that area of work resonates with us all. So George's talk, the title's behind me, continues on the theme of climate change, which is the theme of the workshop today. And having read some of his commentary around global warming, and whether society is better responding to that challenge as a hedgehog or a fox, I have absolutely no doubt that this is going to be a really relevant and interesting talk. For me personally, I was fascinated to read George's abstract because he mentioned three things that are a personal passion for me: the challenge of climate change and making sure that our science informs that challenge and how society responds to it; rugby, I was born in New Zealand, and the movie Invictus, which is actually one of my, I think is a great movie. So I'm really looking forward to George's lecture. So please join with me in welcoming Professor George Philander as our 2015 Priestley Lecture.
Thank you very much, Helen, for the kind words. I'm not sure all of them are true. You'll find out. It's a privilege to be invited to give the Priestley Lecture. I did not have the honour of meeting Dr. Priestley, but I was much intrigued by the short biography that appears in the programme, and in particular his involvement in World War II. And I will start by saying I regard that as an endorsement of the statement, I think it was originally made by somebody in the 19th century, that war is too important to be left to generals. And Dr. Priestley, I'm sure, would have endorsed that statement. His legacy is far greater than Helen mentioned. The contributions of people such as Dr. Priestley to World War II impressed leaders in various countries, and I'm under the impression that the CSIRO here and also in India, and I know for a fact in South Africa, they were motivated by the contributions of scientists to the winning of World War II. And it's hard to imagine today, but there was a time when parents wanted their children to be scientists. And it was an honourable thing to do. And nowadays, it's far more difficult to persuade the youth that science is interesting. And we face an uphill battle. And I want to paraphrase the statement that war is too important to be left to generals, to saying that the future of planet Earth is too important to be left to climate scientists, that we need to get everybody involved. And it's in this room, there's no doubt everybody's concerned about global warming. If you were to step outside, I doubt you would have more than 50% of the people agreeing with you. And the unfortunate thing is, over the last 20 years or so, we've made enormous progress in global warming science. The percentage of the public that believes us has remained at 50% approximately. In rich countries, it's not changed, despite increasing evidence that there is cause for concern. The situation is actually worse. Psychologists, some friends in the psychology department, they conduct polls, and they'll make a statement such as the universe is 14 billion years old, and discover a certain percentage of people will agree. Then they change the statement slightly. They'll say, astronomers tell us that the universe is 14 billion years old, and the percentage that agrees drops. And in the case of global warming, if you conduct the same poll, the drop is even bigger. And so nobody knows a scientist, nobody knows an astronomer, only very few in number. And the moment you say an astronomer or a scientist said something, people get suspicious. They must have an agenda. They want more funds. They want more resources. And so their support decreases. So it's a remarkable change from the legacy of Dr. Priestley to what we have today. And so we have a very serious problem. And the topic is completely polarized. In the US, politicians, when asked about global warming, will declare that I'm not a scientist. To my dismay, our president, whom I greatly admired, Obama, when he was asked about global warming, he did something almost as bad. He said, I'm not a scientist, but I know scientists. And to me, that's not good enough, that everybody ought to know some science. Everybody ought to participate in this discussion. And the fault, I feel, I hate to say this, is entirely ours. We teach science frightfully poorly. And so we teach in such a way we have a polarized situation about a very serious problem. And for guidance, we can turn to a person who dealt extremely well with the polarizing problem, Nelson Mandela. He inherited a country which was on the verge of a civil war when he became president, and he earned global admiration, respect for preventing that from happening. And so we can ask exactly, what did Mandela do that succeeded in South Africa being a peaceful place, completely peaceful transition from apartheid era to post-apartheid? And I would argue that Nelson Mandela was a fox and not a hedgehog. And the reference is to a poem written ages ago in ancient Greece. And there's a book by Berlin, a very short book that analyzes this line. And he basically argues you could probably divide people in this room into two groups. Those who have very firm principles, beliefs to which they adhere in solving any problem. So the hedgehog is animal. When whatever problem he faces, he has one strategy. He rolls up in a ball of spikes. That's the end. On the other hand, a fox is circumspect, looks around, tries different strategies, will adapt his tactics. And my main message today is I have to be careful, and not everybody's going to agree, is that we're behaving a bit like hedgehogs in our approach to global warming, that we need to become more like a fox. So you may want a specific example. What did Mandela do exactly? And I'll go to Helen's favorite movie. You can watch the movie Invictus to find out. So Mandela inherits a country. At the time, the fear of a civil war was so great that on the order of 1 million people left South Africa, all young, all highly educated, in a country where the government had neglected to educate the populace. And so this was a major disaster, having these people leave. I must confess I'm a bit more nervous than usual in giving this talk because I'm about to say a few things with which probably not everybody's going to agree. But I hope we can have a discussion afterwards. Anyway, so Invictus nominally is about rugby, but it really is a movie about the importance of symbols. Mandela discovers that there's going to be a rugby tournament in South Africa, and politicians do this all the time. He wishes to use this sports occasion to bring unity to the country. As I said, many people try it. The challenge in South Africa is that rugby is a symbol of oppression. It's a game played by white youths. And the bizarre thing is the game black youths play is soccer. The bizarre thing is the one is played with a round ball and the other one with the oblong ball. To the uninitiated, that's the main difference. Nonetheless, this can lead to enormous animosity between different groups. Mandela has his work cut out. The members of his party, the ANC, are strongly opposed to the government having anything to do with this rugby tournament. And so Mandela has to overcome that opposition. He also has to persuade the rugby team, it was a mediocre team at the time, that they should really do their utmost to win this game, that it's in the interest of the country that this game be won. And so the movie is actually fascinating. It's particularly worth seeing for portraying the social life in South Africa at the time, for that matter, at the moment still. So I do recommend you see it, not just for the rugby games, but there's a lot more to it. And it tells a thrilling story. The mediocre team wins the tournament. And there's unity. And the exercise was repeated in 2010 with the World Cup soccer. And the South African soccer team has no white players. And nonetheless, again, the effort was made. Could a poor country coordinate, manage such an enormously complex event? And they succeeded spectacularly. Anyway, if we were to turn, you can ask, how did Mandela succeed? What was the secret in getting the ANC to support this white rugby team? And you could say Mandela democratized rugby. He asked the white players to go to the slums. You cannot love that which you do not know. So you really have to know something about the game, the rules, the players, the strategies. Mandela, when the movie starts, all he knows about rugby is that white people are fanatical about it and black people detest it. And he took the trouble, he learned about the game, and in the end persuaded everybody else likewise. So his advice to us would be that we need to democratize science. Science at the moment is perceived as elitist, very boring and dull, extremely difficult. And we somehow have to persuade people at large that that is not true, that science is fun. It may sound like a straightforward task, but I'm going to show you a short video that to underline how enormously complex it is to convey scientific information to people. This is a short video, and we're only going to watch 2 minutes. And I particularly wanted to pay attention to the statement by the last girl to speak in this video.
Sorry.
Candidate in art.
Despite a lifetime of the very best education, students in our classrooms are failing to learn science. Many of these students will graduate from college with the same scientific misconceptions that they had on entering grade school. To test how a lifetime of education affects our understanding of science, we asked these recent graduates some simple questions in astronomy. Consider, for example, that the causes of the seasons is a topic taught in every standard curriculum.
Okay, I think the seasons happen because as the Earth travels around the sun, it gets nearer to the sun, which produces warmer weather, and gets farther away, which produces colder weather, and hence the seasons.
How hot it is or how cold it is at any given time of the year has to do with the closeness of the Earth to the sun during the seasonal periods.
The Earth goes around the sun, and it gets hotter when we get closer to the sun, and it gets colder when we get further away from the sun.
These graduates, like many of us, think of the Earth's orbit as a highly exaggerated ellipse. Even though the Earth's orbit is very nearly circular, with distance producing virtually no effect on the seasons, we carry with us the strong, incorrect belief that changing distance is responsible for the seasons.
I took physics, planetary motion, and relativity, and electromagnetism, and waves.
I've never really had a scientific background whatsoever, and I got through school without having it. I've gotten very far without having it.
I had quite a bit of science in high school,
Anyway, so what we see that the movie is
Regardless
become
of
very
their
well
science
known.
education,
There are videos about the
21 of
video.
the 23
There have been
who
conferences
selected
about it, what's
students
gone
for
wrong with
faculty and alumni
science
with
education. And the
misconceptions when asked to
bottom, if you, they interviewed 23 students and 21 of them gave the wrong answer. This they were graduating from, I hope Stephen doesn't mind my saying so, after it was expensive education money can buy, that they went to Harvard. I'm quite sure that if you were to conduct a similar survey at Melbourne or Princeton, the results would be the same. That we do a terrible job in teaching science. And I'm particularly intrigued by the statement by the last girl. And so when she realizes she'd given the wrong answer, her response is, it has not handicapped me in the least. That she got into Harvard, she's about to graduate, she has a job on Wall Street. Why are we so insistent that people should know an esoteric fact that the Earth's axis tilts? Why is that important? Why, in general, do we want people to know science? I'm using PowerPoint. I have not the foggiest idea how it works. Most of you have cell phones. We can use the products of science without knowing any science. Why is it so important? We just need a few. We don't need many of these scientists. And they produce these amazing results. How do we persuade this girl that she should know some science? And I'll divide my talk into 3 parts. I'm calling her Alice because she needs to be introduced to a wonderland, and the wonderland is science. And we have to persuade her that it's to her benefit to learn some science. And to do that, I'll divide my talk into 3 parts. I'll try to persuade Alice that science is really organized skepticism. And then the second part, I'll talk about science as poetry. It can enrich your life. It's not just there for practical benefits. And the last part is probably going to be the most controversial. This is a paraphrase of something Galileo supposedly said when he had troubles with the Pope. I think the original statement was that the Bible teaches us how to get to heaven. It doesn't tell us how the heaven, or how to go to heaven. It doesn't tell us how the heavens go. And I would say science is the opposite. And I want to make sure how much time there will be, that we have enough time for this, because this is a serious limitation of science. It does not tell you how to live your life. Science is mute on ethical issues, which means whereas science demands of its practitioners a firm commitment to skepticism. And this puts us in a bind, because it means that scientists wear 2 hats. To live an ethical life, you have to have some beliefs, you have to have some principles. You cannot go around questioning everything. There must be some things you assume as everybody accepts. On the other hand, to be a scientist, you should not accept anything you're told. You have to be skeptical. Listening to the talks today, I should be careful with my words. I'm not sure that everybody realizes this, that we have to be skeptical. It's not clear to me we're adequately skeptical in our approach to our science. So let me start with the first one. What's most amazing about this video to me is it brings to our attention that science is taught poorly, and it does so in a manner that exacerbates the problem. It gives the impression that science is a collection of facts and theories. And you either know the answer or you don't. And there's a game called Jeopardy that's similar. And you ask the question, and if you know the answer, you're considered smart. And if you don't know the answer, you're dumb. And I would submit science is not that at all. That science is a continual interplay between facts and theories, between observations and theories. And we could go through this exercise. I'll go through it briefly and play the game for the question, why is summer warmer than winter? So we can start with an observation. Suppose I'm Alice and you are the observationists. You present me with a fact. And the fact is that summer is warmer than winter. And you ask for the explanation. And I will think about this for a minute and confidently answer that the Earth's orbit is an ellipse. We're sometimes closer to the sun than other times, and that's the reason. So then your response should be to go and check this fact. So you're going to make some measurements. You discover that the Earth's orbit is indeed an ellipse. We are sometimes closer to the sun, sometimes further. And you go back to Alice and you tell her that I have some good news for you and some bad news. And the good news is that in Melbourne, the Earth's orbit is an ellipse. We've checked that. And the Earth is closer to the sun on the 3rd of January. That's perihelion. And so the good news for you is in Melbourne, it's summer on the 3rd of January. Your theory must be right. However, the bad news is that there seem to be many places where this is not true, where summer actually occurs in June. Cambridge, Massachusetts is one of them. And so how do you cope with this? So now it's Alice's turn to respond. And being from Harvard, she's very clever. She goes away for a little while. She comes back and says, I misspoke the first time. there are actually two reasons for the seasons. One is the Earth's orbiting ellipse, and the other one is that the axis tilts. And they check, and indeed, this seems to explain. It introduces fascinating new concepts, Tropic of Cancer, Tropic of Capricorn. It introduces dates. There's now a date for solstice, summer solstice, winter solstice. And all goes well, and then Alice insists that these two reasons she's now given can explain many facts, that since Melbourne has a summer for two reasons, its Earth is close to the sun, and the Earth's axis is tilted the right way. It's the reason why our summers are so unbearably hot. And so any number of tennis players can confirm this.
It gets cold in the winter.
And so Alice says we can check this.
The sun in the summer.
That the reason the summers are so hot is
in the fall.
we actually have two reasons. I watched some of my siblings, my brothers, play with the top. And when the top is
seasons affect the way
vertical
everything
and the top is
grows
spinning,
and changes
nothing much
every
happens,
year.
the top spins.
So the reason we
However, the
have
moment
seasons
you
on
tilt
Earth
the
is
axis,
the Earth
the top
is
starts
tilted.
precessing.
Now let's say that this is
And
the
so
Earth,
she said,
and there's an imaginary line going through the middle of it called the Earth's axis. It's tilted, and it stays tilted as the Earth.
Now doing sound.
oh. Okay, that's fine. So anyway, she says that she checked that if you play with the top and you tilt the axis, that's not the end of the story. The axis starts precessing. And she's made some calculations, and she's discovered that the Earth, because its axis tilts, precesses, and that it completes a precession cycle in about 20,000 years. That means if people in Melbourne, so what's significant about that, there are dates associated with both the tilt, which is the solstice, and with the eccentricity of the orbit, which is perihelion. Today they coincide, but 10,000 years ago, perihelion would have been in June. And so the northern hemisphere would have had summers that, for two reasons, were extremely hot. If people were playing tennis in Melbourne 10,000 years ago, it would have actually been quite pleasant. And she can prove this. And so she proposes we can go to archaeologists or paleontologists, ask them to dig into the past, find out what Melbourne was like 10,000 years ago. An easier place to go is the Sahara Desert. So basically two reasons for the season. 10,000 years ago, northern summers would have been extremely hot because two separate factors both contributed. If you go to the Sahara today, it looks like that. And it turns out if you were there 10,000 years ago, or if you were to go 10,000 years hence, it would look like that. And so the Sahara had lakes 10,000 years ago. And it's simply because the sun was so hot that the monsoons were far more intense. And so today, the Sahara is this desert, but 10,000 years ago, and paleontologists find bones for crocodiles and giraffes, all sorts of animals that you don't find in the Sahara today. You can find. It's an interesting period, 10,000 years ago. It's shortly after we invented agriculture. And there was quite heavy traffic across the Sahara. You could cross by horseback because there was water, plentiful water available. If you go a bit north of the Sahara to this little island of Sicily, you see these amazing stripes. And it turns out whenever the Sahara has these lakes, the water will run off into the Mediterranean, make it anoxic. The water becomes so stable. Mediterranean is really salty, but if you pour fresh water onto it, there's no mixing. Those are the dark bands, or maybe it's the light one. Anyway, the other ones are the light. And if you date these, it turns out to be 20,000-year periods for that. So this notion that the seasons are really there for two reasons turns out to be correct. So you can find out about the past by drilling into this land or drilling into the seafloor. You could go further, and when people have gone all over the globe, drilled into the seafloor, and you learn a great deal about past climates. And in particular, this is a record for the last 5 million years, and the astonishing thing you discover is that we're at the most precarious moment at the moment, at the present, a most precarious moment in the history of the planet. We're right there, that little tip. And if this were your own information and you ask what's going to happen next, you'll say this ice age is imminent. Those peaks, those are called interglacials, so these are recurrent ice age cycles. And it's a disturbing picture. They've been getting bigger and bigger. They were small, regardless as a measure of temperature. And there's been a cooling trend and these enormous oscillations. So at this time, much of the globe, much of the northern hemisphere is covered with huge glaciers. They melted quickly. The interglacial periods do not last very long. So those are the interglacials. And this current one could be on the verge of ending. However, if you now gotten into the habit of digging, you can also go to Antarctica and dig into the ice and get this record. So you can see this is a completely different record from this is digging into the sea floor. And I've gone back to the dinosaurs. Every schoolboy is an authority on the dinosaurs. Almost nobody knows the amazing story of what happened subsequently. At this time, there was no ice on the planet. It was too hot. These are temperatures near the poles. Earth cooled off. This has to do with plate tectonics, the drifting of continents. It's actually a marvelous story as to how we ended up there. We Homo sapiens appear at the late stage. We don't amount to much, but we take off there. Then if we go to the ice core, we get more detailed records. Everything we've accomplished, from invention of gardening, invention of agriculture, to farming, to civilizations, everything was in this little period. We developed so rapidly that we became capable of that. That's the CO2. So I could argue that it's an inadvertent consequence of our astonishing progress, that in 10,000 years we should be able to get to that stage, take off. We were around during the previous interglacial. It didn't amount to much, couldn't do anything. We survived the next ice age and we took off at this stage. So we can now ask what global warming, scientists will then tell us, is going to lead to global warming. So there's now a competition. I know some, Freeman Dyson is a well-known physicist. I've heard him make the statement that this may be a good thing because we're basically, we're inhibiting the next ice age by pumping in the CO2 into the atmosphere. There's a problem with timescales. The ice age will take a few millennia. We're doing this in a few decades. We have to sort this problem out. So at this stage, we conclude that we're in a very special moment in the history of the planet. We're at the interglacial. They don't typically last long. We've taken advantage of it and we've done that. We could also, if we're so special at this time, there seem to be lots of planets around. How special are we? And we look around, the planet's far more spectacular than ours, but this very modest one over there, planet Earth, is so far the only one known to be habitable. The story becomes even more remarkable in the light of NASA's recent findings that there literally are billions of planets out there. Of those billions of planets, there's precisely one that's habitable, that we know to be habitable. It's this one. And so it behooves us to try and find out what makes us so special and what's going to happen next. And in a very recent copy of the Proceedings of the National Academy of Sciences, there's a paper by a IPCC group where they use their models to simulate the last, I think, 10,000 years. 10,000 is when we were at the peak. And they find that in the models, the warming continues over 10,000 years to the present. But the people who provide the data tell us that the Earth has been cooling off. Okay, that the Ice Age literally has come to an end. I'm excluding the last century, but on this very long time scale, they find this. At this stage, let me go back to, we get two different answers. The modelists tell us global warming started 10,000 years ago. Actually, you can even go further. Their models run for the last 10,000 years, but you could argue since the last glacial maximum 20,000 years ago, it's been warming the globe. The modelists insist in their models, the part they simulate, that is indeed the case. There's been warming. But the observationists claim the Earth has actually been cooling for the last, I think it's 6,000, 7,000 years, until we get to the last few decades. Let's just go back for a moment to Alice. So what has Alice learned up to now? Well, she's learned that a little learning is a dangerous thing. And when Alexander Pope made that statement, he didn't mean that he didn't try to bless ignorance. He was saying that in science, once you learn a little bit, there's no stopping. It's addictive. You want to find out more. There's no end to it. And this game, the interplay between observations and theory, is absolutely fascinating one, and we should make laymen aware. Once they get involved in this game, there is no end to it. One question leads to the next, and things become more and more interesting. It's not a dull game where you either know the answer or you don't. It's a game in which you should persist, and commitment to skepticism is what keeps you going. Whenever you have a new observation, generates a theory, you should go back, check the theory is correct, which leads to more measurements, more theories, and you'll find the landscape expands constantly. Secondly, of what I would agree with this girl that knowing that the Earth's axis tilt is rather sort of a useless esoteric thing. Why should you know this? That, however, what you should learn from science is that there is merit in questioning your beliefs and your assumptions. And it doesn't matter if you're a pastry chef or a taxi driver. You should try new recipes. You should try new routes to see if you pick up more customers. Don't be a hedgehog and do the same thing over and over. Be a fox and try different things, And it builds self-confidence. Right? And I would submit that the main purpose of education is self-confidence. I got involved in South African educational program, and the apartheid tried to destroy self-confidence. I decided that Earth system science, Earth science, trying to explain why the planet is habitable, is an excellent vehicle for getting people interested in science, teaching them. And South African landscape is spectacular. You can climb mountains, see the temperature drops, one side is dry, wet, and so forth. The biggest compliment I had is from a professor at one of the black colleges, much of South Africa is still segregated, who told me he could tell which of his students had been to one of these workshops. It was the students who asked questions when they came back. Science is usually taught that anybody who asks a question must be dumb, and so students are discouraged from asking questions. But just telling them that science progresses through questions, through skepticism, is probably the most valuable lesson to learn from science. And then, so let's move on to what should Alice learn next. And as I said, we're now left with, what do I have here? So we have two approaches. So science is poetry in the sense that it proceeds on the basis of us finding unity and diversity. So we can look at any number of diverse phenomena, objects, and reduce them to a few fundamental principles. And so we greatly admire Newton, Einstein, Darwin for identifying those principles. And it gives a beautiful unity to a great diversity of objects. It's basically what poets try to do. And if I had a cup and I was holding it by its handle, I could refer to the handle as the ear, and I'd be a poet. Right? The cup it's not a body part, but I see a unity between the shape of the handle, or I could say the table has legs. Anyway, poetry enriches our lives, and I would submit that likewise with science, that is a beautiful phenomenon, that the problem with saying we should know a scientist and they'll give the answer, the students at Harvard who did not know why summer is warmer than winter knew less than a Paleolithic farmer. And the trajectory of the sun across the sky changes. If you watch carefully, it becomes quite a marvelous experience to pay attention to what's going on around you. And we've somehow succeeded in suppressing the sense of wonder about what happens outside. That you go to classrooms and people tell you and you believe what they say, and you divorce it from what is experienced outside. And so I feel that our field, we've been rather negligent in that we deal with the most astonishing objects, phenomena, and we've been negligent in pointing out the wonder in these phenomena. In my department at the moment, the most popular course is a course on data analysis. And everybody wants to work for Google or Facebook or whatever. What you need is skills to analyze numbers. And so I'm absolutely shocked students come to our department not to learn about phenomena, to learn how to analyze numbers. And I feel it's negligent of us that we should make them aware of these amazing phenomena. I'll come back to that in a little while. So we have two approaches to this problem. The one is what we call reductionist. And if Newton was asked how does a planet move around the sun, he writes down an amazing equation, introduces a force in which few people believed at the time, gravity, but we accept it because his agreement between observations and theory is so spectacular. So this is a reductionist approach. On the other hand, if you ask how do we know there were ice ages, it's a completely different, it's a holistic approach. Or if you ask how do you know the continents drift, you don't write down an equation and voila, you get an answer. You look at errant rocks, you look at scratches on the rocks. You integrate all this information. It's a beautiful synthesis. You relate it to glaciers that flow, and you come to the conclusion that glaciers ebbed. And so we've come to an understanding, another reductionist approach is to ask, so we now know a lot about the history of the planet. One astonishing thing is the planet has been habitable for 3 billion years. What was the reason, how did it maintain that? And we start with the reductionist approach. So our planet is habitable, Mars is not, Venus is not. It could be that we're the right distance from the sun. Venus is too close, Mars is too far. I assume everybody in the room is familiar with this. The only assumption you make is a conservation of energy. You start with a bare rock, you calculate the temperature, and you quickly discover it's not the distance from the sun that's the only important factor. It's also the albedo. You take into account the albedo and you get the wrong answer still. The albedo tells you how much sunlight gets reflected. And from this wrong answer, you make an astonishing inference. You gather that the atmosphere must be producing a greenhouse effect. And you can even get an order of magnitude for that greenhouse effect from this incorrect answer. So science operates in a beautiful manner. In the reductionist part contributes. We can go into water vapor and so on. It's amazing how quickly you can explain to people why there is huge uncertainty in global warming predictions. It's one word, clouds. Clouds reflect sunlight, meaning that they cool the planet. Water vapor is the most powerful greenhouse gas, which means it warms the planet. For the world of today, the warming loses to the cooling. The net effect of clouds is to cool. The big uncertainty in future global warming, we have no idea what the clouds will be like. And how are we going to solve that problem? I know many people today gave us projections what's likely to happen and so on. Huge uncertainties in those results. One serious problem we face is that over the last 20, 30 years, there's been no progress in reducing uncertainty in what's called climate sensitivity. If we double CO2, how much will global average temperatures increase? 20, 30 years ago, there was a certain range. Today, the range is the same. We've made no progress on that problem. I would submit that the challenge we face is lack of data. We have data for the climate of today. I would submit the climate of today has not changed in the last 1,000 years or so. And we've developed models that we tune to get the right answer. But it also means we're at risk of getting the wrong answer if the climate changes. Right? So there are serious grounds for questioning our projections for what will happen in the future. And it's all because of clouds, because of water vapor. So how can we solve this problem? Let me just... I want to get back to this third part, so I have to finish this quickly. But the main thing in these workshops I mentioned in South Africa, I call them habitable planet workshops. And our planet is habitable because it recycles everything. If you start with the clouds, where they come from, the water comes from the ocean into the clouds, onto the land, back to the ocean. That recycling is true for everything, for carbon dioxide, for oxygen. To appreciate it, you need to know something about atmospheric science. You need to know something about ocean circulation. You have to need something about the solid Earth, plate tectonics. You have to need, above all, about the biosphere and how important the plants are for photosynthesis. And I find it astonishing that we expect of every educated person to know how the human body functions. Everybody, not just in this room, everybody in Melbourne can tell you about the role of the lungs, the liver, the heart, and so on. They know about hygiene, washing your hands, your diet. What's amazing here is nobody is smoking. Barry and I am old enough that we both had a common director of a lab who was famous for sitting in the first row with a huge cigar. And this was considered an admirable thing. We've progressed a lot. We accept that people have not the foggiest idea why the planet is habitable. It's really quite unacceptable. We should demand that of schools, universities, everybody who graduates should know something about each of these systems, should know something about the atmosphere and so on. We can go off on that. Just to get back quickly to the problem of how are we going to improve our climate models, I would submit that we need tests. And it comes down in the end to marrying what I call reductionist and holistic approaches to science. Our biggest success in that area is weather prediction. Weather prediction up to World War II was holistic, incredibly complex maps, rules of thumb, what does low does, what does a high do, what does a warm front, a cold front. Then something radical happened, a computer was invented, and an entirely different way for predicting weather emerged. Write down a few equations, solve those, and that can predict the weather. Fortunately, when the first computers were invented, they were so poor that people had to simplify them enormously, severe reductionism. And they were forced to ask simple questions. Why is there weather in the first place? It led to baroclinic instability theory. How predictable is weather? Led to Lorentz, that sound simple equations. I would argue that what's sadly lacking in climate science is a reductionist approach. Right? So everything here is being basically holistic. I showed you the rocks, the scratches and rocks and so on. There hasn't been, it turns out if you analyze this, the periods have to do with changes in the Earth's orbital parameters. And so it's an amazing result that what you get from astronomy, these periods, is the same as what you get from analyzing this record. And so this seems to be a vindication of Milankovitch. And this stage, I think, climate science at the moment is an exciting stage because it turns out Milankovitch is wrong in the sense that Milankovitch proposed that glaciers are these isolated phenomena that respond to local sunlight. And he could explain why glaciers wax and wane. Today we have a lot more information, and we know glaciers are... Yeah, the first sentence is long. Anyway, glaciers are not these isolated phenomena that Milankovitch imagined. They're actually members of a suite of different phenomena. Wherever we go around the globe, we find Milankovitch cycles. You can look at the sea surface temperatures off Melbourne or in the tropical Pacific. could look at rainfall wherever we have records. And I would propose that what's happening is that glaciers are members of a suite of different phenomena, different parts of the globe. Each of those phenomena is responding to variations in sunlight. Right? Variations in sunlight are not confined to 60 north in June. They're changing all the time. And all these phenomena are interacting. So basically the question that Milenkovic initially posed, what causes ice ages, has become intractable. It's extremely difficult. And the key to any progress in science is to ask the right question. And so I would propose we need to ask a different question, and the different question would be, what is the response of the planet to this precisely known forcing functions? So it becomes very much like the seasonal cycle. The seasonal cycle induces different phenomena in different regions, and we're still struggling with it as to how to, with the many facets of the seasonal cycle we cannot explain. It has a huge regional variation seasonally. In Melbourne it rains in winter, in Mandela it rains in summer, and in northern part of Australia I'm sure it rains in summer and so forth. Some part it rains throughout the year. Globally averaged, there is no seasonal cycle in the rainfall, and we cannot explain that. All these different regions know about each other. So anyway, I want to stop here, but just comment, I gave a seminar about this on Tuesday, that to me, climate science is at as an exciting stage today as weather prediction was in the early 50s. Right? So the most beautiful papers in weather prediction was really in the 1950s, 1960s. Then weather prediction has advanced to this marvelous point where the marriage of the reductionist and the holistic approaches are so excellent that the models are tuned on the basis of measurements, but the models can tell you when the measurements are errant. Right? If there's a station that gives wrong information, the models will tell you. Can we do the same for climate? And I submit that's the challenge. And I would submit that we can do it by focusing on these recurrent cycles. We can discuss that afterwards, but I want to move on to the third part of the talk. Just one quick thing, I can't resist this. I've said the present is the most unusual moment in the history of the planet. And the question is, if you were to step outside, what would you look for? What is it that tells you this is an unusual moment? So you could argue, and it's I said polar regions. That's quite unusual in the history of the planet. I will argue that another remarkable fact today, observational, is this bottom picture, that we have cold water at the equator. You would never guess, if you knew nothing about sea surface temperatures, you'd never guess that you'll find cold water at the equator. The ancient Greeks thought the equator would be so hot you couldn't cross it. And so we live in this unusual world. The same thing as we've developed models. The top world is much more obvious. And there's evidence the top world prevailed. It was the state of affairs up to about 3 million years ago, that there was no cold water at the equator. The same thing is we've developed models that reproduce this bottom state. And when they try to simulate the top, cannot. We've tuned them to get cold water at the equator. So we've actually developed models for a very unusual world, and they're not capable of reproducing a much more obvious world. And it leads to fascinating scientific issues. Under what conditions could you have worlds such as that? But those interested in the technical, we can come back to that later on. What I want to do is turn to this last part of the talk, which is probably the most difficult one. Why is science mute on ethical issues? Others can ask. Right? I was saying science has very severe limitations. It doesn't tell us how to live our lives. And Isaiah Berlin, the fellow who wrote the book about the Hedgehog and the Fox, wrote somewhere that if at the beginning of the 1900s you had asked historians to anticipate the two major developments of the next century, they would have gotten one right and one wrong. And so I can ask you, so the one everybody would have gotten right is easy. It's the technological advances. Right? So they may not have anticipated cell phones or laptops at that time, but they would have anticipated enormous progress in electronics. Electricity was well established, medicine, in transportation. It wasn't a difficult prediction to make in the 1900s. Anybody want to guess what is the prediction nobody would have gotten right, in Berlin's opinion? Sorry? Something much bigger. I'm sorry? No, it's the rise of ideologies. Right? And nobody would have anticipated the fascists, the Nazis, the communists. It cost tens of millions of people their lives. Nobody would have anticipated apartheid. And Berlin sees a connection between the two. And he says that science, the progress in science, is so spectacular that we should look into how it was achieved, and maybe we can use the same methods for social problems, for political problems. So in science, we make postulates. I mentioned Newton, Einstein, Darwin, and then we test those repeatedly, and we refine them. So Einstein's refinement of Newton and so forth. And the results are spectacular. And science is a very cold, cruel activity in that there's no room for compromise. So if you say 2 + 2 is 6 and I say it's 8, we don't settle for the difference. We're both wrong. So science is basically a hedgehog activity, that there is a right answer to a problem, and we can find it by sticking to the laws of physics that we've identified. So suppose that you're a politician, you admire this greatly, and you consider yourself the Darwin of social science or the Newton of social science. You come up with some rules and regulations, laws that everybody should obey. Anybody who disagrees with you is impeding progress, and you end up with a Stalin or a Hitler. Berlin goes forth and says it's not all that difficult to identify the laws that should govern our social lives. We're all for equality, we're all for freedom, we're all for justice. However, the moment you want equality, you cannot have the wolves terrorize the lambs. Right? You cannot have the weak suffer from the strong. You have to compromise. You can insist on justice, but you need to compromise. You need to be compassionate. You need to be forgiving. The social world is all about compromise, seeing somebody else's point of view. And that's where we need a Mandela. So Mandela could take into account in the rugby team. He was aware what it meant for the whites to have a rugby team. It's victorious, what it meant. It's a quality that's sadly lacking. At the moment, everybody seems to know what the answer to some social problem is. And they're absolutely adamant. There's no room for compromise, for taking into account different points of view. Let me see what else I have. The problem, I was going to say, the problem, the Pope and Galileo had a fight. And I would submit it's nothing compared to the trouble we face. So Galileo said that the Earth is rotating around orbits the sun. Upset the Pope very much. He thought the Earth is at the center of the universe. If the Pope were to change his mind, it would have no practical consequence. He'd have more accurate maps and calendars. There was no particular ethical issue at stake except the authority of the church. I would claim that global warming is a far more complex issue, and that it raises ethical issues such as this top one. And how do we find a balance between our responsibilities to future generations and our obligations to those suffering today? So I'm impressed by Australia a very wealthy country. I've not seen any homeless people. I've not seen slums, nothing. Visit Africa. It's another story. I would submit that global warming is not a priority to Africans. That if you don't know where your next meal is coming from, why on earth should you worry about things 50 years hence? How do we bridge this? One of the worst meetings I went to was an IPCC meeting in Africa. The goal of the meeting was to discuss how Africans can best be assisted in coping with global warming. We stayed in a fancy place like this, and to get to the conference center, another fancy place, we had to drive in a bus past slums. And slums there are shacks, absolute shacks. At the end of this meeting, the recommendation from this distinguished scientist who gathered was that what Africa needs is a server with a geodel model output. I couldn't believe this. That these people tend not to see what they don't want to see. You've decided beforehand, and it's not easy. So as my main message is, global warming is not an easy problem. We shouldn't pretend that it is. I had several references to an Australian politician I gather who's skeptical about global warming. I admit we need to engage him. It's going to be difficult. Think of Mandela. He engaged people with whom we bitterly disagreed. It takes leadership. I'm not sure what it takes. I have one recommendation. And so I'll show you this. As I started these workshops, and these children are from a high school in slum, and there's no transportation to speak of, so they've never been to the beach, even though it's a short distance from where they are. Cape Town is around Table Mountain, they've never been to the top. And I persuaded them science is fun, take them to the top of a mountain. And taking them to an archaeological, anthropological, there's some digs, fossil digs, where you can show that everybody originally was African. To a black African student, this is astonishing news. It boosts self-esteem, education. As I said, self-confidence to me is the main goal of education. The main thing, the last part is a quote from the Librarian of Congress, Princeton. And he pointed out that the obstacle to progress is not ignorance, it's the illusion of knowledge. We should be more willing to admit that our models may have problems, have errors, to constantly be knowing what's going to happen. My main point is that in my experience of Africa, you cannot tell poor people, so poor that they don't know where the next meal is from, you cannot tell them that the future is going to be worse. That's cruel. You have to tell them the future is going to be better. You can tell them we have to be optimistic. They're fortunate we're the only planet that's habitable. It is an absolutely astonishing planet. We should use our field not so much to train more Earth scientists, but to use it as a vehicle for education. And if every child has a thermometer and is told to monitor the most astonishing thing that happens, which is the annual seasonal cycle, they'll quickly learn about graphs, they'll learn some statistics, they'll learn to use Excel. So the main goal is not so much to teach them earth science, it's simply use earth science as a vehicle to teach them skills that are very badly needed. So I have a specific proposal I'd like your opinion on. This is a picture taken in 1969, first picture of planet Earth from the moon. And the anniversary, 50th anniversary, comes up in 2019, in 4 years. And so I've approached our National Academy of Science and proposed, this is not in competition with concern about global warming, nothing like that, that 2019 become an occasion to celebrate planet Earth. And it's an amazing picture. We are hanging there, all it gets is sunlight, it maintains habitability conditions. The only planet we know of that is habitable. Right? What happened after we took this picture is a bit discouraging. We immediately got interested in Mars, and then in the Hubble Space Telescope and other galaxies. But I think we need to remind people to go back to that period, look back. And so it should be an optimistic message. I think there's too much gloom and doom. All the terrible things are going to happen. So I don't say we should stop that. There's a role for that. But there is a need for a complementary approach. And so I'm hoping through our National Academy of Sciences that they can approach the Australian Academy of Science. It has to be done at a high level. Have a global celebration for a whole year. And the goal is to, if nothing else, to tell people the story that comes along with that picture. It's actually an amazing story of the history of our planet. You can introduce any number of things. During the first part, the continents were drifting. During that time, exotic mammals appeared in the savannas of Africa. Then the Ice Age started. If this were the vital signs of a patient in a hospital, starts with a high fever, we get it under control, then he has these convulsions. We would rush into the emergency room. This is our planet. We've done remarkably well in explaining a good deal. We've now reached the stage where it's quite exciting in the science. We have to marry. All of this information is obtained holistically. As I said, there's not been much reductionist approach to this. So I feel the science is an absolutely exciting stage. It's something we can get laymen interested in. I ask your support. Thank you.
Oh, thank you, George. I'm actually going to take a few questions. I know the program says response, but I wouldn't dare to dream that I could say anything that matched what you've just been talking about. So what I'd like to do is take a couple of questions and then I'll formally bring us to a close. So I think Simon was first, then Mike. Simon.
George, you spoke about our commitment or our obligation to future generations. Economists expect that future generations will be richer than us, as they have been over the last 150 years or so, much richer, much more technology, etc. Does that make us like the slum dwellers and they're the rich IPCC people at their hotel in the future? And we don't have so much obligation?
Yeah, I'm not sure this is an answer, but they have a name for that. It's the discount rate. And what's interesting about the discount rates, if you look at, there's an American economist, Nordhaus, and there's a British one, I've forgotten, the one who worked for Tony Blair, Lord something. They would take exactly the same scientific information and produce quite different results as to what should be done. And it was all on account of a different discount rate. If you face a problem 50 years hence, you should discount the cost of it because you're going to be much smarter 50 years hence. For the poor, the discount rate should be huge. They're going to, we hope, much better off. To the rich, they already have enough. And so they tend to discount, make a very small discount rate. But that's exactly the type of issue we get into. What should the discount rate be in our projections for what's needed in future? Depends on whether you're rich or poor.
Mike?
Yeah, thank you very much for the talk. Just wondering where we should look for the leadership in the example you gave, Mandela taught himself the rules of rugby and then used the rules to manipulate things, whereas you seem to be advocating that we as scientists should teach the public about science, whereas is the model we should find a capable politician to educate in science to
No, I tried it on the fellow drove me to Aspendale this morning. I told him what I'm going to tell you and asked what suggestions he has. And he told me, contact Jackman, an actor. And he said, he's a virtuous, honest man. We need, for a start, we're hopeless at communicating. Why not get some excellent actors? I mean, we have amazing stories to tell. We tell it to each other. We don't tell it to the world at large. Something like the seasonal cycle is absolute miracle. If you look at it, we take it for granted. I feel it needs to be a coordinated effort. But I think the leaders will come forth. I must say I have much more confidence in the youth than I have in people my age. If you get old, you get very set in your ways. But the only success I had in South Africa was with the youth. Mm-hmm. They would accept. Mm-hmm.
I'm going to take one more question. Peter, back.
So, George, you separated science and ethics right at the start of your talk, but I think by the end you'd actually converged them again, suggesting that as science we have a message to tell, and it's looking that we live very, very much so on the caring for our planet. And I just wanted to, I'm sure you know about this, but I know that there's a branch of neuroscience that's starting to say that ethics is actually open to scientific interpretation. There are rules around ethics that are universal and have evolved with us in our brains. I've only done a little bit of reading around that. I found it pretty fuzzy, but I also found it quite exciting that the whole question of ethics might be open to the kind of scientific investigation that we as physicists do
You have lots of confidence in science. I'm of the opinion there are some problems that do not lend themselves to scientific solutions. There's a play and there's a paper called Tragedy of the Commons, and I highly recommend it. It has to do with some village having a commons, and when the population is small, everybody can have their cattle graze there. There's no problem. However, at some point, overgrazing becomes a problem. And at this stage, if any one farmer adds a few more animals to his herd, he gets all the benefits and everybody has to pay for the possible damages. How do you persuade this farmer that he should take into account other people's needs and so forth? So this Tragedy of the Commons was cited as an example of a problem that is not amenable to scientific solutions. It requires us to come to some communal agreement on what it means. We can talk after. There's been a long history. In the 60s, there were people at Stanford who carried on about overpopulation and how by the end of the century there's going to be riots in the streets and lack of food. It didn't happen. But in the 90s, one of the very right-wing people challenged them to a bet to identify 6 commodities that would rise so steeply in price that there would be havoc on the markets. And these very left-wing people took on this, and they lost the bet. And there's recently been a book. So the right-wingers' argument was that our biggest asset are our brains. Whatever problem we have, we can find solutions, which again becomes a philosophical issue. It's not just a matter of having these commodities. What kind of world do you want to live in? Right? So you may be able to find solutions to certain problems, but we have to take into account like a bit of nature preserved and so on. My main message is there's a whole suite of problems which do not lend themselves strictly to scientific solutions. And global warming is one of those. You certainly need to know some science to appreciate what's going on. Once you know that